very useful. Okay, without further ado, let me introduce Sasha Sodin, who will tell us about quasi-one-dimensional random operators.
Okay, thank you very much. It's great to be here. It's a nice place. I attended one Midrasha back in 2009 as a participant. It was very beneficial for my mathematical education. It's great to be here again. So I've been asked to give a survey talk, and that's what I'll do. And let me first define the object. So we fix a number W, a natural number, which will play the same role as in Jonathan Stock. If you are new to the subject, you can focus on the case W equal to 1 without losing much in the first half of the talk at least. We'll consider the space of square summable sequences taken values in CW, so vector valued square summable sequences. Again, for W equal 1, these are usual square summable sequences. And we consider the operator H acting on a domain of the space in a similar way to that in Jonathan Stock. The jth element of H psi is minus psi of j plus 1 plus Vj psi of j minus psi of j minus 1, where these are this is a sequence of independent, identically distributed Hermitian matrices. Is the setting fine? At each, for each j, I have a W by W matrix, and this is how the operator acts. Okay? When W equals 1, these are just numbers. So equivalently, you can think of it as an infinite block diagonal matrix. It's block tree diagonal, so there are blocks, W by W blocks on the diagonal and on the two diagonals adjacent to it. So for when W is equal to 1, this is called the one-dimensional Anderson model. And for larger W, it contains a number of different models, including the Anderson model in a strip and some other models which about which you may hear in Tanya's talk later. So the base equation is of spectral type. In order to avoid terminology, I'll just ask the most basic question. Does H have an orthonormal eigenbasis? So just to appreciate the question, let me just make a remark that for when all the v's are when the v's are constant, then the answer is no. And in fact, when the v's are constant, the operator doesn't have a single eigenfunction, not to speak of an orthonormal eigenbasis. So the reason is that for this v, or in fact for any v, we can consider consider the eigenfunction equation, the equation which an eigenfunction should satisfy, minus psi j plus 1 plus v j psi of j minus psi of j minus 1 equals lambda psi of j, where lambda is the spectral parameter, which should be the eigenvalue. And in the case when Vj are constant, it's not hard to see that any solution to this equation is either exponentially growing or not decaying. It can never go to zero, both at plus and minus infinity. So we can't have even a single eigenfunction. Right? As opposed to this case, if we are properly random, the situation is completely different, and the main fact, I'll give references later, but this is somehow the summary of the research in the 70s and the 80s, is that under proper assumptions, excluding the case of degenerate distributions, the answer is yes. So H has, with probability 1, an eigenbasis, and all the eigenfunctions are not just square summable, but in fact exponentially decaying. And my goal today is to explain what these proper assumptions are, state the main result properly, explain what is the general strategy of the proof, and also state some open questions which were somehow not solved in the 80s when this subject was more active. Okay. Any questions? So the spectral theory of this operator starts from this eigenfunction equation, and the basic observation from first year linear algebra course is that we can set up a matrix, a 2W by 2W matrix, which takes psi j minus 1 to psi j plus 1. So psi j plus 1, psi j, this is a vector in R. 2W is obtained from the vector psi j minus 1 by multiplication of a matrix, which you can easily write down, Vj minus lambda times the identity minus the identity 0. I'll denote this by Tj of lambda. It's if you look at this matrix for 2 seconds, you will see that the determinant of this matrix is equal to 1, so it lies in the spatial linear group. That's what you can, for W equals 1, that's it, but for larger W, one can strengthen this, and in fact, Tj of lambda preserves the quadratic form 0 minus 1, 1, 0. Which means in fancy language that Tj lies in the symplectic group. Again, for W equals 1, this is just a special linear group. And it's, this is an important point. It's somehow a reflection of the fact that the operator is self-adjoint. Therefore, we can continue this equality. So psi j plus 1 psi j is obtained from the initial conditions psi 1, psi 0 by multiplying j of these matrices, Tj of lambda up to T1 of lambda. These are, I'll denote this product by phi j of lambda. Is this phi j still visible back there? And we see that for any fixed lambda, this is a kind of random walk. It's a product of independent random matrices in the symplectic group. So it's a kind of random walk in the symplectic group. and the question is, what can one say about this? So I'll first, so here there's a special feature that the steps depend on an additional real parameter lambda. Let me first remind you what is known without the parameter, and then explain how this parameter comes in. So definition, let Tj in the symplectic group. Again, if you are new to this, think of W equals 1. This is just 2 by 2. These are 2 by 2 matrices of determinant 1. Be independent and identically distributed. And then we look at their product. And we ask, how does it grow? The most basic question is, how does the norm grow? And on exponential scale. So the top Lyapunov exponent is defined as the limit as j goes to infinity of 1 over j times the expectation of the logarithm of the norm of phi j. So it's a kind of, well, at least it measures how does the norm of phi j grow on exponential scale, but then it's natural to consider the next singular values too. So we define gamma r to be the limit of 1 over j times the expectation of the logarithm of the rth singular value of phi j when r is 1 to w. From not very complicated standard theory, these are also almost sure limits, meaning that with probability 1 we can erase the expectations. Okay. One thing I should say, which has to do with the symplectic structure, is that remark there is a symmetry here. So, for example, gamma 2w is equal to minus gamma 1, and gamma 2w minus 1 is equal to minus gamma 2, and so forth. This is an easy consequence of the symplectic structure. For example, for w equals 1, the product of the singular values is 1, so if there is one growing exponentially, the other one should decay exponentially. So now returning to our setting of the transfer matrices of the Schrödinger operator, it's very desirable to have gamma w greater than 0. Why is it desirable? So suppose this is the case, let's say for all lambda, then what do we expect? That there's, I mean, they come in pairs. So if w Lyapunov exponents are positive, the other w are negative. So we expect our 2w-dimensional space of initial conditions to split into to contain a w-dimensional space for which the solution decays. Now, you see, we want our solution to decay exponentially both to plus infinity and to minus infinity. So we have a w-dimensional space of initial conditions for which the solution decays in one direction, another w-dimensional space of solutions which decay in the other direction, and generically two w-dimensional spaces are not supposed to intersect. However, we have this extra spectral parameter which we vary, and therefore we can at least naively expect to have a zero-dimensional set of lambdas for which these two spaces do intersect, and these will be exactly the eigenvalues. Of course, if gamma w is equal to 0, then we would need an even less generic event to get any eigenfunctions, and it's very unlikely to happen. So kind of the natural, well, it seems very reasonable that we need this in order to get the theorem which we stated, and therefore that's what we'll discuss now. Any questions? SR is the rth singular value.
Oh, thanks.
So in the 60s, Fürstenberg provided a sufficient condition that ensures that the top Lyapunov exponent of a random matrix product is strictly positive, which is sufficient for W equals 1 and not sufficient for larger W. As it happens, all these conditions are of algebraic nature. It's unlike the case of random walk on R, where the case whether we have positive velocity or not somehow has to do with the expectation. The way here the condition is algebraic. We need to consider the group G generated by. So I mean this is in the setting of this definition. Let's consider the group generated by the support of, let's say, T1. So all the walk takes place in our group. And the theorem is that if this group does not preserve any probability measure on, let's say, the projective space. You can think of the sphere if you like. Then the top Lyapunov exponent is positive. When this doesn't look very explicit, but in fact it's explicit. One can check. It's easy to verify. So for W equals 1. Our matrices look like this, so it's an easy fact that for any pair of real numbers A and B which are not equal to one another, the group generated by A minus 1, 1, 0 and B minus 1, 1, 0 is okay. Does not preserve any probability measure on the projective line, and therefore if in this case of W equals 1, if the potential is not constant, if we rule out this case which the degenerate case, then the Lyapunov exponent is strictly positive for all values of the spectral parameter. In the case of larger W is more complicated, and there is no, at least I don't know, an explicit condition of this form. What is known, and this is a result of Goldshade and Margulis from the late 80s, is this visible? It's a very important theorem, so I would like to have it in a visible place. Goldshade and Margulis. For W greater than 1. We want to ensure that gamma W is greater than 0, but in fact they provide a sufficient condition to ensure, which ensures that all the exponents are different from one another. So gamma 1 is greater than gamma 2, greater than gamma W, greater than 0, provided that this group G is Zariski dense. So if you are, so you shouldn't be scared of this word. It basically means that the group, that there's no algebraic equation satisfied by the matrix elements of each element generated by the group. If you should rule out the case when any element of the group has an the same algebraic relation between the matrix elements. Once you ensure this doesn't happen, all the Lyapunov exponents are different. Now it's somehow one can ask whether these are consistent, and indeed it's an easy exercise. Well, an instructive exercise to check that if G does preserve probability measure, then it is not Zariski dense. Okay. I will come to check. So in this case of W greater, this condition is harder to verify than this one, and there was a work of Goldscheid in the early 90s. Already Goldscheid and Margulis showed how to verify it in some cases, and later Goldscheid provided criterion which contains almost all the models which I am aware of. So Goldscheid, I think 93, and he stated the following, that the group G generated by a bunch of matrices of the form of this form V minus 1, 1, 0, where V varies in some set, is Zariski dense in the symplectic group, provided that, okay, we need to exclude trivial cases. One trivial case is when all these matrices have a joint invariant subspace. So then the model itself splits into. Then this operator has a deterministic invariant subspace. It somehow splits into a sum of several operators. This is not very interesting. So let's assume that V is irreducible, which exactly means that all the matrices in V don't have a joint invariant subspace. And also want to exclude the case when V is not random, so we have to assume something. What Goldscheid assumes is that V contains two matrices, V tilde and V double tilde, which differ by rank 1. So in simple words, if you have a reducibility and this matrix has one random element on the diagonal somewhere, then you are fine. The Lyapunov exponents are all distinct from one another and are positive. Okay, so now, so let me call this condition plus. Now I can state the theorem. So special cases were proved by Goldscheid in the early 80s, before this theory was well developed. The current form for W equals 1 is due to Carmona, Klein, and Martinelli, again building on earlier work starting from Goldscheid, Molchanov, and Pastor. In the case of larger W is due to Klein, Lacroix, and Spice, and Goldscheid, Margulis. They've stated it under more restrictive assumptions, so the current assumptions incorporate this result of Goldscheid's problem. And the statement is that if you assume this condition on the distribution of the potential, then almost surely H has an orthonormal eigenbasis, and moreover each eigenfunction decays at plus minus infinity exponentially exactly with the rate prescribed by the wth Lyapunov exponent, which we've defined earlier. So for each, I need some notation. Let me denote by psi k the eigenfunctions and by ek the eigenvalues. So then each psi k decays at infinity. The limit, let's say lim sup, as j goes to plus minus infinity of 1 over j times the logarithm of the norm of psi of j. So the rate of decay at plus minus infinity is at least minus gamma w at this ek. So the eigenfunction at ek decays with the rate. Oh, I'm sorry. Is this this is not visible? Lim sup of 1 over j times the logarithm of the norm of psi k of j is less or equal than minus gamma w, the wth Lyapunov exponent, evaluated at ek as the eigenvalue. Yeah. So not only we have exponential decay, but we know exactly how fast it is.
Is it complete eigenbasis?
An eigenbasis is an eigenbasis. An eigenbasis is a basis is an orthonormal.
Of entire space.
Yes. That's an eigenbasis is an eigenbasis. Yes. All the time. Now let me tell you what is the strategy of the proof, or more precisely, let me tell you why the proof is not obvious, or what is the main obstacle to the proof. So, how does the proof work? As usual in spectral theory, we start from the eigenvalue, from the eigenfunction equation, and it's a kind of general fact that in spectral theory we are interested in solutions of moderate growth. If we would know in advance that the spectrum is pure point, we would only look at square summable solutions. However, we don't know this a priori, so we look at solutions which satisfy growth most linearly. There's nothing sacred about this linear growth. The main point is that exponentially growing solutions are irrelevant in spectral theory. So the goal is to prove that any solution of this kind in fact decays exponentially at plus or minus infinity. So for fixed lambda, one can upgrade. So we know that the singular values, half of the singular values grow exponentially, the other half decay exponentially. We can upgrade this a bit. Let's say for 2 by 2 matrices, we have an exponentially growing singular value and exponentially decaying one, but perhaps the initial condition for which you get decay is different for different j's. So the theorem, the fundamental theorem of Otselides shows that it's not the case. That one can find, so almost surely there exists a subspace of Rw, of R2W of dimension W, for which, so that if you take any initial condition of in the space, you will get exponential decay, such that for any x in f, lim sup of t logarithm of tj x divided by j is less or equal than minus gamma w. So you can there is a j-independent space in which have the dimension in which you have decay. So the naive idea of Anderson localization could be as follows. Basically what I've tried to sketch earlier in this talk. we have a W-dimensional space F of initial conditions which decay at plus infinity, and we have another W-dimensional space, let's call it F minus, of which of initial conditions for which we get decay at minus infinity. Generically, they don't intersect, but then okay, we have we vary lambda, so we get a set of exceptions, and these are the for which we have decay both at plus and for which there's a common point here. Then you have decay at plus and minus infinity. And if you're not at these special points, then you just don't have, then any solution has to grow exponentially at least in one direction, and therefore it's irrelevant. So this should somehow prove that any solution lives exactly at these special points and decays in both directions in the right way. So the problem is that this is not quite correct, and the reason has to, so the reason, and I'll write it in red since it's the main danger here, so it's a result of, at least for W equals 1, the basic idea is due to Goldshade, then it was generalized many times and rediscovered and extended to matrix co-cycles, but again, the main idea is already there, and it says the following, that almost surely, so you see, the problem is that this holds for a fixed lambda, and there are uncountably many lambdas, so you can't use the union bounds. It sounds a very technical problem. Perhaps you just have to kind of approximate carefully to some epsilon net argument, but it turns out that almost surely there really is a set of exceptional lambdas for which not only this, but the entire theory fails. So there's a set of lambdas for which the jth, let's say liminf, the jth singular value does not grow exponentially at all. The wth singular value by j of lambda does not grow exponentially at all. And this set is in fact topologically huge. It's residual G delta dense in the spectrum of our operator. G delta dense in the spectrum of our operator. So exactly outside the spectrum, all the theory is uniform and nice, but in the spectrum, exactly where we need it, there lambdas for which exponential growth fails, and you can see that if your spectral measure, our spectral measure gives any weight to these sets, then you really can't have any result of this form. So the dangers, okay, quite well understood already by Goldshade, were further explained by Alexander Gordon, who used this this circle of ideas to show that one can take our model, perturb it by a rank 1 perturbation, so something which is usually very benign in spectral theory, and destroy this property. So the perturbed model won't have a single eigenfunction, not to speak of a complete eigenbasis. Of course, the perturbation will depend on these VGs, but so it's really a disaster. Any questions? Pardon?
For which model is this Goldshade? What is VJ?
VJ is the J-step transfer matrix. Yes, this yeah. For this yes. It's yeah yeah, it's very, one can say some words abstractly for random matrices depending on a parameter, and say some words such as non-uniform hyperbolicity, but the point is that the only case when at least I am able to check this condition is when the matrices come from spectral theory, and then it's exactly the spectrum where they're non-uniformly hyperbolic. So what what this means is that basically the challenge here, this theorem is equivalent to saying that the spectral measures avoid this nasty set. So, I mean, you can prove it in different ways, but this is what the theorem says, and somehow something like this appears in any proof of localization, although it can be disguised in different forms. Any questions? So that's what I wanted to say about the proof, and now I would like to discuss some questions. So this theory was developed in the 80s. The last result was from 1990. There was some more recent activity which I would I think Lana Zhytomyrskaya deserves the credit. The original proofs were somewhat complicated and used multi-scale analysis and following vehement, eloquent advice of Lana, and also her own work. New proofs were found, which are quite elementary. But essentially, all this was known in 1990. However, some questions remained, and I would like to discuss them briefly, if you don't mind. So in this theorem we have an inequality. The rate of decay is at least as fast as the wth Lyapunov exponent prescribes. Okay, we can't have equality here. Even for w equals 1, there is no reason why an eigenfunction can't vanish at a point. But it's more reasonable to look at the vector of psi of j and j plus 1. So let me state this as a question. Is it true, is it almost surely true, that for any k you have equality once you make these minor corrections? The limit as j goes to infinity of 1 over j times the logarithm of, let's say, the maximum between psi k of j and psi k of j plus 1 is equal to the minus to gamma w of k, which is the same as plus gamma w plus 1 of k. So common sense and the genericity arguments which I've tried to sketch indicate that this should be the case, but the problem is as far as I understand. So let me explain you what is true, and what is true and easy, not hard, and what is hard. So the result of Goldscheid, which I've erased, says that the wth singular vector can be much smaller than the Lyapunov exponent prescribes. It turns out that the situation is not symmetric, so it's not that it can jump down and jump up, and this has to do with the fact that polynomials can easily do this kind of thing, be large and have a zero at one point, but very rarely, or never do they are they allowed to have upward spikes. So Craig and Simon proved many years ago, and that let's say the norm cannot be larger than prescribed by the Lyapunov exponent. So probability 1 for all lambda lim sup of 1 over j times logarithm of the norm of phi j of lambda is less or equal than gamma 1 of lambda. Okay. So the top singular value cannot be larger than it should be. So in the case of in the case of w equals 1, there is just one Lyapunov exponent, and this shows that it can jump down but not up, and therefore, right, the second singular value cannot be smaller than minus gamma 1 because their product is 1. So what this means is that regardless of eigenvalues in spectral theory and initial conditions, there are just no solutions of this equation which decay faster than e to the than with rate gamma 1 of lambda. Right, that's what this means, and therefore the answer to this question is positive in for w equals 1, which is observed already by Craig and Simon. Is this fine?
I'm sorry, I'm a bit confused. Wasn't the limit of this the definition of the?
No, so all this game is with quantifiers. For any lambda, of course, the limit is equal to gamma 1. However, you can't have it simultaneously for all lambda. What Craig and Simon show is that exceptions are in one. The lim-inf behaves irregularly. The lim-sup behaves regularly. In fact, in this case, there's equality here in this AD case. So this is very general. In the AD case, one can prove that there is equality here. So for w greater than 1, what this shows for w greater than 1, what this shows is that if we denote this quantity by star, is that lim sup lim inf of star is greater or equal than minus gamma 1 of lambda. And you see the lim sup, we know that the lim sup is less or equal than minus gamma w, and of course we expect the answer. We expect the answer to be gamma w rather than gamma 1. There's a great gap between this and what we expect. I mean, in the generality of the theorem which I've stated, I think this is all what is known. Under regularity assumptions, if the distribution of the potential is nice enough and so forth, one can improve this slightly. Basically prove that this is a strict inequality. I mean, there's an explicit lower bound which is strictly better than this, and also one can show that for lim sup of is equal to minus gamma w of lambda. So at least on the subsequence, the behavior as it should be. These two appear in recent work with Ilya Botchit. Okay, the general cases. So this is very far from satisfactory, and the problem is that we don't understand well. We know that the behavior of the singular values is not uniform, but while for the wth singular value we understand the structure of the exceptional set, for other, we don't understand so well how the exceptional sets look for the other singular values. Even in the case of 4 by 4 cocycles, w equals 2, we know that the second singular value can jump down to 0, and we know that the top singular value can't jump up, but we don't know whether the top singular value can jump down. If we would know that it cannot, then we would be able to prove this conjecture, at least under the regularity assumptions. So missing better understanding of exceptional sets, and there are reasons to study this question which are also beyond the scope of this talk. So there are other reasons to study it as well. Okay, so now there are 5 minutes remaining, right? So I would like to mention the most interesting open question, which should have probably deserves 45 out of the 50 minutes of my talk. But since I haven't worked on this so much, especially recently, I will. So the reason why it got a side place in my talk is only due to my limited competence. And this is the question. So of large W. So the problem is that these results of Goldscheid-Margulis and all the other results are with the algebraic conditions are not very suitable for getting explicit estimates, and even for the simplest case, corresponding to the Anderson model in a strip, where VGA is by itself a W by W three-diagonal matrix with random variables on the diagonal, let's say standard Gaussian random variables on the diagonal, it's not clear. So the Goldscheid-Margulis theorem provides no hint as to what the asymptotics what the behavior of the Lyapunov exponents for large W is. So, for example, for this case, the conjecture is that gamma W is bounded from below by a constant divided by W, and the best result I am aware of due to Bourgain is something like e to the minus W times log to some power log squared W. So you see, there is a huge gap between what is known and what is expected. Bourgain has a very nice proof, but it doesn't capture the reasons why the argument has nothing to do with the mechanisms which we believe are responsible for this behavior, and say getting a power law lower bound for this model would be extremely interesting. So as far as I know, there's no progress on this for many years. However, there is some interesting progress on other models, and I think of this type, and I think you'll hear about some of this in Tanya's talk on Thursday. So don't be afraid of the Jerusalem day or whatever, and stay until. Okay, so I think I've told everything I know on the subject. Thank you very much for the.
Thank you, Sasha. Questions? I have a question. Can you give some intuition as to why this is supposed to be the lower bound? Why it has to be C over W?
Okay, so there is what the physicists do. They try to construct an you start with a strip and they try to construct an effective proper 1D system which somehow has the same behavior. So you can you integrate over the irrelevant variables, and you. So there is a procedure which tells you how to do this. If you so you know for 1D weak disorder, we know the asymptotics very well, and this procedure tells you how the width renormalizes the disorder, and it turns out that it does it in such a way that it's roughly 1/square root of the disorder. So that's one of the explanations. I am not sure it's extremely convincing, but definitely the answer should be power law, because what else? What else could it be? Yeah.
I was just wondering if it's reasonable to look at some of the sigma values from numerical experiments. Is that possible?
Yes, yes, I believe this is a tractable numerical problem. I think, unlike other things such as Anderson localization in 2 dimensions, where you expect at weak disorder, where you expect the localization length to be exponential in the inverse disorder, and it's probably untractable. This I believe is.
That sounds like nobody's tried yet.
I believe some people did try. I believe physicists tried this, and
What did they see?
You say that it's correct. They even have prediction for this C. More precise. This in some
yeah, I mean, I should have. I'm sorry. I should have mentioned that there is another explanation, which is via supersymmetric field theory. One can also map it to supersymmetric field theory, and then again, mathematically, it's very different from the ones which can be analyzed rigorously. But physically, if you integrate over if you ignore the irrelevant variables, then it becomes very close to things which can now be rigorously analyzed. And this one. There's lots of work on that, included by Young, and it gives consistent predictions.
More questions? Well, if not, let's thank Sasha again.